is about motion of a charged particle in a magnetic field. Charged particle means now we will take the positive charged particle. We can accelerate the negative charged particle also, but in the application like a large hadron collider or any type of accelerator, normally we use positive charged particles. If we take the negative charged particle, the problem is that the negative charged particle like electrons, they are very light particles. So if we try to accelerate them, very soon they will go out of control. Their mass is so small, right? The mass of the proton, right, which is 1.67 multiplied 10 raised to the power minus 27 kg, that is so suitable mass which can be accelerated very smoothly and it can be controlled also. I mean, it can be given a fine circular path by the electromagnetic field. But if we use the electron, then very soon it will go out of the radius, right? So the radius cannot be controlled easily in case of the negative charge particle. But if we use the proton, positive charge particle, then it is easy to control the radius. Okay. So now what happens when a charged particle like proton enter in a magnetic field? Okay. So let us take a magnetic field, and normally we represent the magnetic field by these crows. So these crows, they represent the inward magnetic field. Inward means the magnetic field going inside the bond. So they are inward magnetic field. So this is the reason of inward magnetic field. And inward magnetic field, that is B in, right? And magnetic field that can be shown by a vector also, right? So magnetic field is going inside the board, and our charged particle that will come from outside and that will try to move inside the magnetic field. So assume we have a charged particle here. This is a charged particle, and this charged particle now trying to move inside the magnetic field with some speed v. So the charged particle, this is the proton, and the charge of the proton, that is equal to 1.6 into 10 raised to the power minus 19 coulombs, and the mass of the proton is 1.67 multiplied 10 raised to the power minus 27 kg. So with this mass and with this charge, the particle is trying to enter inside the magnetic field. So you see here the particle is entering at an angle of 90 degree. So it's a normal entry. Normal entry means entry at 90 degree. So what will happen? So in that case, if we check the force, so definitely this magnetic field will apply a force on the charged particle, right? And that force can be given by the equation. So the force on a charged particle, inside the magnetic field by a magnetic field, we can say by a magnetic field, that can be given by the equation F is equal to, we have this equation, the magnetic force F, that will be equal to Q V B sine theta. This is magnetic force. So I will say this is FB, magnetic force, right? So the magnetic force is given by this equation. F is equal to Q V B sine theta, and where Q is the charge, on the proton, V is the speed of the proton. Speed is so slow now. It's not a high speed, it's a normal speed, right? And B is the magnetic field, already inward magnetic field. Sine theta means the angle with which the particle enter inside the magnetic field. So there are four factors on which the force on the charged particle will depend. The force will depend upon the charge, how much charge we are sending into the magnetic field, the speed of the particle entering into the magnetic field, the value of the magnetic field, and the angle with which the particle is entering into the magnetic field, right? So the four factors, they control the magnetic force. If we increase the charge, means if we enter two charged particles, right? if we throw two charge particles inside the magnetic field, definitely the force will be more, right? So overall, the magnitude of the charge that will decide the force also. Second thing is that if we send the protons with a very high speed, so again in that case means the high speed particles they will face more magnetic force, right? And the third thing, if finally we increase the magnetic field, means if we send the particle with a very powerful magnetic field, again the magnetic force will be more, right? And then angle also. So I will focus on this part. I will focus on the angle. This part, this sine theta. This sine theta. This is important for me, right? How by changing the angle, right? You see, if we increase the charge, right, we need more and more charge. We need more and more protons, right? So that is again a challenge for us. If we increase the speed, again we need some device. I need some device. If I want to increase the magnetic field, I need powerful magnets, super magnets. So these three things, they are expensive. They will add cost to our accelerator. They will add expense to our accelerator. So the easy method to increase the magnetic force, that is the angle, that is the trigonometry. So by this theta, means if we change the angle, that doesn't pay any extra cost, right? So just by using the mathematics, we can increase the magnetic force. We need not to make, we need not to increase Q, V, B. Means these three factors, they decide the cost to the accelerator. But just by changing the angle, just by focusing on the mathematics, we can increase the magnetic force, right? Now, how that happens, let us understand the mathematics behind that. Now, this force that can be increased by increasing the Q, increasing V, increasing B, and increasing sine theta, right? So, if sine theta become maximum, in that case, FB will also become maximum. And the maximum value of sine theta, is equal to 1. The maximum value of sine theta is equal to 1 when theta is equal to 90 degree, right? So in that case, sine theta means sine 90, then it becomes 1. So from all these mathematical interpretations, we can understand if we project the particle normally in the magnetic field at an angle of 90 degree. So in that case, our particle will be under the maximum magnetic force, right? So now if we place theta is equal to 90 degree, so what we will get? So theta is equal to 90 degrees and 90 is equal to 1. Now the magnetic force acting on the charged particle, that will be Q V into B. And this will be the maximum magnetic force, right? Maximum magnetic force. So this is the magnitude of the force. This is the maximum magnitude of the force acting on the charged particle. But along with the magnitude, we are interested in the direction also. What is the direction? Right? And what this force will do? What this force will do? When the charged particle enter into a magnetic field, we have the magnitude of the force. Now this much magnetic force will be there on the charged particle. Now what this force will do? Right? So let us check that. So suppose this particle enter slowly in the magnetic field, right? With the speed v. Now you see, initially when the particle was outside the field, it was a linear motion, right? It was moving in a straight line. So we assume that again in the magnetic field it should continue with the same straight line path, right? But the magnetic field that will apply a magnetic force, from the right hand rule we can find out the direction of magnetic force. So the thumb that gives the direction of motion, the thumb, okay, so thumb that gives motion means that gives speed, speed v, okay. And the first finger that gives direction of magnetic field, direction of magnetic field. Magnetic field. Magnetic field means B. And the central finger, that will give the direction of, that will give the direction of force, right? That will give the direction of force. Direction of this force, right? Direction of this force on the charge particle. Direction of force. Which force? Magnetic force. Magnetic force means that will give the direction of Fb is equal to QVB. So the central finger will give the direction of this force. Central finger will give the, so this is from the central finger. This is from the central finger. Central finger. So now you apply the Fleming, you apply your right hand. So the magnetic field is inward, the particle is trying to move in the right side. So upward force will act on the charged particle. Again, you see at this point the particle is trying to move up. So magnetic field is again here in this direction and the particle is trying to move up. Okay, and so in that case the direction that will be in the left side. So again the path will be changed and it will move in the left direction. Now if you come to this point, again at this point the magnetic field is inward, particle is trying to move in the left direction, but the force that will be the downward direction. So from here it will try to move downward. So finally it will be a circular path. It will be a circular path. Now what will be the radius of the circular path? We will find out that. But before the radius, you see this force is trying to move the particle in a circular path. It means this force is type of a centripetal force, right? So this force is actually trying to move the particle in a circular path. So this force is behaving like a centripetal force, and centripetal force that can be written as mv square upon r. So this is the centripetal force, where m is the mass of the charged particle, v is the speed of charged particle, and r is the radius. R is the radius of the circle, right? So now we have two equations, call it 1, call it 2. So actually this magnetic force that is trying to take the particle in a circular path, and we say if it is a circular path, means force is trying to take the particle in a circular path, so it means definitely that is a centripetal force. So now we can say the force is acting towards the center, the centripetal force Fc, and the centripetal force acting towards the center, that is mv square upon r, right? So that is acting towards the center due to the centripetal force. Every time, everywhere on the locus of the circle, every time the force is toward the center, so that's why it is known as the centripetal force. Every time this force tries to take the particle in a circular path. Okay, so because Fb, the magnetic force, is producing the Fc, the magnetic force is producing the centripetal force. Now I can compare these two forces. So now by comparing these two forces, comparing equation 1 and equation 2. So if we compare equation 1 and equation 2, so I will get Q V B will be equal to mv square upon r. mv square upon r. So I can cancel v by v. So the radius, I will get the radius that will be equal to mv by qb. Radius. Now in LHC, you see, we are designing, as an engineer, we are designing the tube of a fixed radius. So from this equation 3 that will help us to make a tube of fixed radius, because our particles, they are moving in a fixed radius. So we want to make a tube. Now I will keep these particles in a tube, right? That will be the LHC tube. So suppose this is the LHC tube. So I need to make the tube of the same radius. Now from equation 3, we have m into v in the numerator and q into b in the denominator. So if we focus on the numerator part, right, on mv. So from this numerator part, from this upper part, m into v, you see the massive particles with a very high speed, they increase the radius, right? So massive particle with high speed, they increase the radius, right? Lighter particle with less speed, they decrease the radius. So if we compare the proton with the electron, mass of the electron is much less than the mass of the proton. So it means if we use the electron, right? So we will get a small radius. We will get a small radius, right? But if you see the denominator part, the means more is the charge, stronger is the magnetic field. In that case, again we will get the less radius, right? So if we increase Q, we increase B, we will get the less radius. If the charge is less, magnetic field is small, then the radius will be big. So depending upon our requirement, the area, the availability of the area, we can design, right? So you see in the LHC, which is at France-Switzerland boundary, the total circumference of the collider is 27 kilometer, right? So total circumference means 2 pi r is equal to 27 kilometer. From there you can find out r, right? So 2 pi r that is equal to 27 kilometer. Now from here you can find out r. So r will be equal to 27 by 2 into 3.14, right? So from here you can decide the radius of your accelerator, right? And that radius, that should match with the mass of the particle, that should match with the speed, that should match with the Q, that should match with the applied magnetic field. How to decide the radius? The radius, that depends upon all these factors, right? So the value you are getting here, based upon that value, you have to adjust M, V, Q and B. Based upon this value, you have to adjust M, V, Q and B, right? Otherwise, if you doesn't match these two values, so the particle that will try to make a hole through the tube, that will try to come out from the tube, that will puncture the tube, right? We want that smoothly the charged particle that just do a circular motion, circularly accelerated motion, right? So that its speed can become comparable to the speed of light finally that we want. And that is possible if we adjust R with these parameters M, V, Q and B. Now radius is done. Now after that we want to find out the time period of rotation, means how much time it will take to make a complete circle, right? So now time period. So time period. So suppose the charged particle start from here, make a complete circle, again come back here. So this is my point P, right? So to make a complete circle, how much time it will need? So that is time to make one round or one circle. So suppose T is the time. So T is equal to distance upon speed. T is equal to distance. What is formula? Distance upon speed. Distance upon speed, right? So T, that will be equal to distance. Distance is circumference, 2 pi r. Total distance means it will move over the circumference. It will move over the circumference. So 2 pi and radius is r. And what is speed? What is speed? Speed is time is equal to distance upon speed, right? And okay, and speed is V. This is the speed V with which it enter into the magnetic field. So this is the speed. Now just putting the value of R, what is R, from equation 3, putting the value of R in this equation, we will get the time. Okay, so just put value of R, put value of R, value of radius from equation 3, from equation 3. So we will get the time. So time will be equal to 2 pi divided by V multiply R, and R is mv upon qb. mv upon qb. V cancel, so T will be equal to 2 pi m upon q into b. And this is the factor which help us to design the accelerator, right? So you see, this is a value, this is the factor, which helps us to design the accelerator, which helps us to design accelerator, particle accelerator, like cyclotron, cyclotron is also a particle accelerator, right? Cyclotron, I will show you the working of the cyclotron through a video. Cyclotron is also a positive charge particle accelerator. So you see, in this T is equal to 2 pi m upon qb, is there anything which strikes your mind? You see, the time period that depends upon 2, a mathematical number, pi, mathematical number, m means time period that depends upon mass, right? Time period that depends upon charge, time period that depends upon the magnetic field applied, but time period that doesn't depend upon the speed of the particle entering into the magnetic field. It is a slow particle, it is a high speed particle, doesn't matter for a time for the time period, right? The speed of the particle entering into the magnetic field, that doesn't affect the time. Very strange. Speed. You see, in our classical world, the time is decided by the speed. The high speed you have, the lesser time you have, right? But you see, if the speed is high or low, that doesn't change the time. So this is the formula which helps the scientists or the engineers to manufacture or to make the particle accelerator, right? So totally independent of speed. So it is independent on speed of particle, right? So it is a high speed particle, it is a low speed particle that doesn't affect the time period. Now we can calculate the frequency of rotations in 1 second, because we are concerned with the energy, right? Energy of the particle moving in a circular motion. So the beauty of this equation is that in this equation of time period, just making a complete round, the time period that is completely independent of the speed of the particle entering into the magnetic field. It is a low speed particle, it is a high speed particle that doesn't affect the time period. So time period is controlled only by the mass of the particle. We are using a proton, so 1.67 multiply 10 raised to the power minus 27 kg. That depends on the charge. It is a positive charge particle. Actually, what is the charge? And the magnetic field, right? Of course, the magnetic field. Magnetic field is also a very important term. But completely it is independent of the speed. So based upon this factor, the scientists and the engineers, they manufacture the particle accelerators, and cyclotron is one of the particle accelerators designed on this equation. So finally we are interested in the frequency, right? Means in 1 second how many rotation the particle can make in a circular path. So frequency, that is equal to inverse of the time period. So what will be the unit? So time is in second, time will be in second, so the unit is per second. The frequency is in per second, or the frequency that is in hertz also, right? It is in hertz also. So just put the value of t, so f is equal to, if I place the value of t, so this qb will go up, and then in the denominator I will get 2 pi into m. So again the same conclusion, the frequency of a charged particle moving in a circular path, that is completely independent of the speed with which the charged particle enter into the magnetic field. Only the magnetic field, the mass of the charged particle, the charge of the charged particle, they will decide, they will control the frequency.
What happens to one?
Which one?
The one, like what
One.
happened? It just evaporates.
Means you place the value of t, this one.
Yeah.
This is just, nothing will happen. Means this one will be multiplied by qb, and finally we will get the qb. Okay.
Sir, could you